Hello and welcome to part 2 of analytical chemistry. In this, we'll be recapping and covering some new information on chemical measurements. So this is a very important part of the analytical chemist's job because it sort of is to do with how much of a particular substance is in their sample. And without careful chemical measurements, the resulting reports that may be derived would be meaningless. So in this section, we're going to be covering things such as SI units, which are the sort of standard scientific units that we use in the literature, that we use in our everyday lives as chemists. Chemical concentrations then, preparing solutions, especially looking at preparing dilute solutions from more concentrated ones. Then we'll be looking at stoichiometry calculations for gravimetric analysis. And then finally, we'll be looking a little bit at limiting reagents. So some of those units that we talked about, those SI units, they're typically the base units that we derive all of our other units from, and they often have particular meanings that appropriated to them, or they are based on some fundamental concept. So the meter, that's our unit of length or distance. From that, we derive units such as centimeter or kilometer. Kilograms are our mass measurement, from which we get grams, we get micrograms, we get larger measurements like tons and so on. Seconds, then, those are our measure of time. We can have milliseconds, we can have longer, we can have minutes, we can have hours, we can have days, and so on. Then amperes, those are a unit of current. We have here Kelvin and K, that's our unit of temperature. We typically use Kelvin in most scientific measurements because it is more reliable when if we go to calculate other constants later. But if we're writing a report for a general audience, oftentimes we will convert that to whatever the local standard measurement of temperature is, whether that be degrees Celsius or degrees Fahrenheit. Typically, it is degrees Celsius. And then the final one is the unit of concentration, the mole, and this has a definition based on Avogadro's constant. So from these basic scientific units, we can derive some others. So these other quantities can be derived in terms of base scientific units. So for example, force, which is often given the term Newton or N, is going to be kilogram meters per second squared. Then the pressure or Pascal is going to be the force in newtons per meter squared. So basically the force over some area. And then energy is going to be the force versus the distance moved. So it's going to be Newton meters. So there are other units which can be derived from these scientific units, but these are just three examples, three of the most common, I suppose. The joule, the Pascal, and the Newton are all derived scientific units and can be brought back to first principles to those previous scientific units that we talked about. Those units, those SI units that we talked about initially, they can have prefixes attached to them. So for example, we were talking there about kilograms or grams. So the kilogram is actually the scientific unit, but it already has a prefix attached to it. It has the prefix kilo attached to it. And this kilo is often a colloquial term for a kilogram. So you can say like, can I have 1 kilogram of my vegetables or whatever, please? And they'll give you a kilogram of that. They will understand that. Now, that prefix can be removed and we can get gram. And so that gram is going to be sort of like a base unit that we can then go back to things like smaller units like milligrams. And so these prefixes are attached. They have a particular symbol associated with them. In the case of kilograms, it's kg. In the case of milligrams, it's mg. So here we have some common larger prefixes and some common smaller prefixes. So these are all smaller. So we have decigram, milligram, microgram, nanogram, and picogram. Typically in chemistry, we deal with grams, milligrams, micrograms, and kilograms. Well, quite rarely kilograms, but usually kilograms in terms of something like a solvent. Mega also is a large one. That's a factor of 10 to the 6. And these can be interconverted just so long as we remember what the particular factors are going to be. So how do we use these prefixes in calculations? So it's a good idea to always write the units with the numbers that we're using in calculations to avoid mistakes, because oftentimes it can be quite confusing once we get to the final answer if we have not explicitly written down our units as we've gone through. Now, in some simple calculations, it's okay to omit them here and there, but generally it's better to keep them at all times so that we don't really run into these confusing moments. Prefixes are used to denote multiples of units. So for example, in the case of kilogram, it means 1,000 grams. In the case of a milligram, it means 1,000 milligrams is going to be a gram. So 1 milligram is going to be 1,000th of a gram. Convert units to common prefixes to help simplify calculations. So for example, if we're dealing with several different length measurements, we have one measurement in meters, we have one measurement in centimeters, another in millimeters or kilometers or whatever, it's often best to simplify that calculation by converting all of the units into one common unit, whether that be centimeters, millimeters, meters, whatever helps you to best solve the problem, unless it has been told to you which unit you should use. So for example, if we have 19.3 millipascals, we want to express this in terms of atmosphere, which is another measurement of pressure, especially derived for gas pressures. So 19.3 millipascals, so this M is highlighted. This is one of our prefixes. It is a smaller prefix, and so we can then write that as 19.3 times 10 to the minus 3 pascals. And so those pascals can be more easily converted to the atmosphere. So we have 19.3 times 10 to the minus 3 pascals times this conversion factor, where 1 atmosphere is going to be equal to 101,325 pascals. And so when we multiply this by this, we get 1.90 times 10 to the minus 7 atmospheres as our final answer. And so we've been able to express this millipascals in terms of atmospheres. So measures of concentration, we have typical measures of concentration here. We have molarity, which we might already be familiar with, which is the moles of solute per liter of solution, and it is given the unit large M. We also have molality, which is going to be the moles of solute per kilogram of solvent. We have the formal concentration, which isn't really used that much anymore, but can still be useful whenever we want to be very explicit in terms of our molarity. And it's good to be aware of it because some textbooks do make use of it. Then we also have percent composition, which is going to be weight, volume, or weight, volume. This is going to be expressed in percent because at the end of the day, it says percent composition. Then parts per million, that's going to be ppm. And then parts per billion, that's going to be ppb. So we'll see how we can kind of come up with these units of concentration shortly. So the first one that we'll encounter is going to be molarity, which is big M. So here we have moles of solute per liter of solution. So our calculation is going to be moles of solute over liter of solution. So the number of moles is going to be the mass divided by its formula weight or its molecular mass. So the square brackets around a species indicates that we're talking about or referring to molarity. So in this case here, we have Na plus in square brackets. So that is going to be referring to the molarity of sodium ions. And it's often important that we are aware of concentrations because whenever we are dealing with injections or we're looking at giving out medicines or something like that, we often want to make sure that we have the correct concentration so that we don't cause any adverse side effects. It's the same in our reactions. We need to make sure that we have enough of a certain substance to ensure an adequate or good reaction. So how do we calculate molarity? So if we have this problem where we have 0.175 grams of ammonium phosphate, which has a molar mass of 149.02 grams per mole, and it is dissolved in water to make a 45 milliliter solution. So the first thing that we do is we find out how many moles this is going to be. So in order to find the number of moles, that's going to be the mass in grams divided by the relative molecular mass, which is going to be, in this case, 149.02 grams per mole, which we had in our question. We could also have worked that out based on the name, But in this case, it's given to us, so we should just use it. So then once we've done that, we find out the number of moles, which is 0.00117 moles. Then we can work out the concentration as being equal to the number of moles divided by the volume. In this case, it's going to be 0.00117 moles divided by 0.045 liters. So we've converted our 45 milliliters into liters. So 1,000 milliliters makes a liter. So we just divide this by 1,000 to get the number of liters, and this is the number of liters. So then once we calculate this, we'll find that our molarity is going to be 5.3 times 10 to the minus 5 moles per liter. So the next one that we'll encounter is the molality. This is small m. So this is the number of moles of solute per kilogram of solvent. So in this case, we're no longer dealing with a volume, we're instead dealing with a mass. So in this case, sometimes this is important in industrial settings where instead of dealing with a volume, which could be variable from one place to another, we're dealing instead in kilograms of solvent, which would give us a more universal measurement. Masses are universal throughout the world and throughout the different environmental and atmospheric conditions, whereas volumes can change. So it's often useful to use this molality, where moles of solute are divided by kilograms of solvent. So a sample problem, what is molality? So if we have 1.5 times 10 to the 3 liters of water, and to this we add 20 pounds of magnesium sulfate. So we're given the conversion of pounds to grams, and so 1 pound, pound is also lb, so that's pounds, is going to be equal to 453.59 grams. So we're dealing with molality here, so we're going to want to also convert our water, assuming a conversion of 1 milliliter to 1 gram. We're going to be looking at 1.5 times 10 to the 3 liters. So we're going to have 1.5 times 10 to the 3 kilograms, because a liter contains 1,000 milliliters, which is also 1,000 grams, which is 1 kilogram. So the solution here is to work out the number of moles. So the first thing we have to do is we have to convert our pounds into grams. So we'll multiply the 20 pounds by this many grams and then divide by 1,109.94 grams per mole, which is going to be our relative molar mass. And so that's going to be equal to 75.6 moles. Then in order to calculate our molality of solution, we're going to be looking at moles of solute divided by kilograms of solvent. And so we'll get 75.6 moles divided by 1,500 kilograms, which is the mass of our water. And so that's going to be equal to 0.050 molal in this case. So formality, this F, so this is the formal concentration. So it's kind of very similar to molarity. They both describe concentration, and in the modern scientific vernacular, what's happened is that formality has been largely replaced by molarity in the literature. And so what we see is that whenever people write down molarity, they're also referring to the formality of that solution or concentration. So formality is the total concentration regardless of species type. And so this is a kind of a more robust definition of concentration than molarity, because it's only relevant if the species dissociate, because molarity of a 0.1 mole glucose solution in water is both 0.1 molar and 0.1 formality, because it does not dissociate. So what this means is whenever it dissolves in water, it does not separate into constituent ions or anything like that. Whereas whenever we're considering a salt, such as sodium chloride, if we dissolve that in 1 liter of water, we would assume that we would have a 0.1 molar solution of NaCl, but formally we don't, because what happens is the NaCl actually dissociates. So there is no more NaCl in solution, at least in this relatively dilute solution. And so we have a 0 molar concentration formally, because it dissociates into 0.1 molar Na plus and 0.1 molar Cl minus. But it has the formality of 0.1 formal concentration of sodium chloride. And this is because formality is the total concentration regardless of species type. So it doesn't Formality doesn't really care that the sodium chloride has dissociated, but molarity, strictly speaking, does. Molarity just looks at the concentration of the particular ions. Now, in saying this, what has happened over time is that whenever we refer to a 0.1 molar solution of NaCl, what we're really talking about is that we understand that it dissociates into these ions. So formality has largely become ignored in modern literature, but it is more or less a more rigorous definition. Percent composition then, so weight percent is going to be equal to the mass of the solute divided by the mass of the total system, or the total sample. So that's going to be times 100% in order to get a percentage. Volume percent is going to be very similar. So it's going to be the volume of the solute divided by the volume of the total solution, and that's going to be multiplied by 100% as well. Then we can look at this ethanol solution, which is 95% volume by volume ethanol. So that means that for every 100 milliliters of solution, there will be 95 milliliters of ethanol. ppm then, so this is the mass of the substance divided by the mass of the sample times 10 to the 6. So what's happening here is that we're kind of expressing a very small concentration. You don't really use ppm or indeed ppb whenever we're dealing with relatively concentrated solutions. There are better options available. So there are also shortcuts to this. So ppm can also be expressed as milligrams per liter or micrograms per milliliter if the density of the solution is 1 gram per milliliter. So this is in the case of solutions in water, which to all intents and purposes, we generally assume is going to be 1 gram per milliliter. So a 1000 part per million copper aqueous solution contains 1000 milligrams of copper per liter of solution. So that's using this conversion where we have a 1000 ppm copper solution will have 1000 milligrams per liter. So if we have ppm is also milligrams per liter, and we could also convert that into micrograms per milliliter if we so wished. So it also contains 1000 micrograms per milliliter of solution. So let's have a look at a worked example for PPB, where we're talking about rainwater, which contains a small amount of heptane, about 46 ppb of this C7H16 heptane, which is an alkane. And so we're asked, what is the molarity of heptane? So 46 ppb is going to be equal to 46 nanograms of heptane per gram of rainwater, which is approximately 46 nanograms per milliliter. So we want to first find the molarity, which is going to be grams per liter. So we need to find out the molarity here, which is going to be 46 nanograms of our heptane per milliliter is going to be multiplied by this conversion factor, which will give us as 46 micrograms of heptane per liter. So based on this, we can now convert this into our molarity by using the molecular mass of heptane, which is 100.21 grams per mole. Then we are looking at the concentration of heptane in the square brackets here is going to be equal to 46 times 10 to the minus 6 grams per liter divided by 100.21 grams per mole, which is going to be equal to 4.6 times 10 to the minus 7 molar. Solutions then, so this is where we're trying to create dilute solutions more or less from more concentrated ones. It's harder to go in the opposite direction. So to calculate reagent quantities for solution preparations, we can use the relation where the molar concentration of the concentrated solution times the volume of the concentrated solution is going to be equal to the molar concentration of the diluted solution times the volume of the diluted solution, which means that if we know 3 out of 4 of these, then we can find the 4th one by simple rearrangement of the equation. So this relationship equates moles of reagent removed from a stock solution to moles delivered into a new solution. So let's do a worked example. So how many moles of hydrated copper sulfate are needed to make 500 milliliters of a solution that is 1000.0 ppm copper? So we'll be looking at the grams of hydrated copper sulfate, and we'll also be looking at the milliliters of 10,000 ppm copper sulfate solution needed to make this solution here, this 1,000 ppm copper solution. So first, we'll be asking how many grams of hydrated copper sulfate are needed to make 500 milliliters of a solution that is 1,000 ppm in copper. The molecular mass of copper sulfate is 249.69 grams per mole. So first calculate the grams of copper required. So that's going to be 500 milliliters times 1,000 micrograms per milliliter. Remember, this is our shortcut for ppm. We're assuming that the aqueous solution is 1 grams per milliliter. So that's going to be equal to 5.0 times 10 to the 5 micrograms of copper. So we can then use this information on the number of micrograms of copper to find out the number of grams of copper. So that's just using our conversion factor. So 1 gram is equal to, 1 microgram is equal to 10 to the minus 6 grams of copper. Then 5.0 times 10 to the minus 1 grams of copper is the number of grams that we need, or it's 0.5 grams of copper. So we can then calculate how many moles of copper sulfate solution, or how many moles of copper sulfate are needed in the solution. So we have 0.50 grams of copper per 500 milliliter solution. So that's going to give us 0.50 grams times 1 mole of copper per 63.546 grams of copper is going to give us 0.0078 moles of copper. So this 0.0078 moles of copper means that 0.0078 moles of copper, hydrated copper sulfate, are going to be in that solution. So this finally brings us on to our final part, where we're going to be using that relationship that we looked at earlier to determine the number of milliliters of a concentrated, that 10,000 ppm copper sulfate solution, are going to be needed to make the 500 milliliters of the dilute 1,000 ppm copper solution. So we're going to be using that relationship that we learned about earlier, which is the molar concentration of the concentrated solution times the volume of the concentrated solution is going to be equal to the molar concentration of the dilute solution times the volume of the dilute solution. So what we have going into this is we have the concentration here, which is 10,000. We have the concentration here of 1,000 in the dilute case, and we have the volume of 500 milliliters of the dilute case as well. And so the only thing that we're missing is this volume of the concentrated solution required to make that dilute solution. So we fill in our values like so, and then we'll rearrange our equation so that we have the volume of the concentrated solution on one side, and then we have all of the known values on the other. So that will give us a volume of the concentrated solution of 50 milliliters. And so the process now that we'll undertake is to make the dilute solution is to place 50 milliliters of our concentrated 10,000 ppm copper sulfate stock solution in a 500 milliliter volumetric flask and fill that up to the 500 milliliter mark. Now, moving on to stoichiometry, we're talking about stoichiometry relationships and how they can be used to calculate required masses or volumes of reagents in chemical reactions. And then the amount of reactant consumed in a reaction can be determined from the mass of the product produced. So if we have so much of a product produced and we know the overall reaction, including any prefixes and ratios of the moles, then we can determine the mass of the reactant consumed. So let's have a look at a bit of a stoichiometry example for an analytical chemistry process. So zinc is often used in dietary supplements and can be measured gravimetrically by dissolving the tablet in dilute acid and precipitating it as zinc hydroxide. So the tablet containing zinc picolinate is first dissolved in water and then filtered to remove any insoluble binders before adding some sodium hydroxide to precipitate out zinc 2 hydroxide. This is then filtered and heated in a furnace to produce zinc oxide, so that heating in the furnace converts it to zinc oxide. But the more important step there is that it's removing any extra water that might be adding to the weight. So the process here is that the zinc 2 plus reacts with the hydroxide to form the insoluble zinc hydroxide, which can then be heated up in a furnace to produce the dry zinc oxide. So in this case, we're being asked to do the gravimetric analysis. And so there's often a minimum sample size required for gravimetric analysis to ensure accuracy. So if each tablet contains approximately 7 milligrams of zinc after the counterion is considered, how many tablets are required to produce 0.25 grams of zinc oxide? So the first thing is we want to know how many moles of zinc oxide are in 0.25 grams. And so it turns out that there are 3.1 times 10 to the minus 3 moles of zinc oxide in 0.25 grams. So we can then use that number of moles to find out the mass of zinc that would be required. And so that would be 3.1 times 10 to the minus 3 moles of zinc. And so we would multiply that by the molar mass of zinc, and we would find out that we would have 0.2 grams of zinc in that many moles. So we can then take this number of moles or this number of grams of zinc and find out how many tablets are going to be required, because we know that each tablet contains approximately 7 milligrams of zinc. So we simply divide the mass of zinc required, which is 0.2 grams, by the number of milligrams, or grams in this case, of zinc per tablet. We find out that we need about 28.5 tablets to create a sample which is large enough in size to ensure accuracy. In our reactions, we often have limiting reagents, and so the limiting reagent is consumed first in a chemical reaction. Total consumption of the limiting reagent stops the reaction. So in a reaction, one reagent is going to be present in a lower concentration than the other, and whenever that reagent is totally consumed, then there can be no more reaction, because the reaction requires all of the reagents in order to proceed. So an example of this, so for example, we have a reaction, A plus 2B gives P, which means that for every A that is consumed, 2 molecules of B must be used up as well. So if we have 0.651 moles of A and we mix that with 1.25 moles of B, then we're being asked what is the limiting reagent and how much excess reagent remains unreacted. So the first thing to do is to check which reagent is limiting. If A is limiting, then we need 0.651 moles of A times 2 moles of B for every 1 mole of A. So that means that we would need 1.302 moles of B. Now we know that we only have 1.25 moles of B present. So B must be the limiting reagent. There's not enough B to consume all of A. So how many moles of A react with B? So if we have 1.25 moles of B, then we multiply that by the molar ratio of A to B. So that means for every 1 mole of A, we need 2 moles of B. So that means that the number of moles of A which can be consumed by B is going to be 0.625 moles of A. This means that there are going to be 0.651 moles of A minus 0.625 moles of A gives 0.026 moles of A remaining after reaction, with all of B being consumed. So in our final reaction mixture, we would have some of A and mostly our product present. This has been the second part of our analytical chemistry process. So thank you for watching. Please comment any questions down below.